We thought maybe your phone died and you didn't have Google Maps, so you couldn't figure out how to get here. That was just our guess, though. Hey, so guys, one of the things that your better teachers do is you sort of always have your finger on the pulse a little bit. What kind of day is it going to be? What is the energy level, the mindset, the level of engagement of the folks in the room? And frankly, for me too, there are days where I'm just like chasing butterflies. And guys, Jared wanted to do an in-depth study, I think, on sleep. And right, guys, I don't know why, but I'm in the same boat. Like last week was a 4-day week. So we should have come back at some level sort of, hey, we're back, we're good, we're rested. This is a 4-day week, then a 4-day weekend, then another 4-day week. So guys, all of the calendar stuff should be saying light and good and energetic days. I'm not feeling it. And I'm getting the sense that you are neither. And guys, you know me well enough to know that I'm good at a lot of things, but being a cheerleader is not one of them, right? And so, but guys, the reality of it is this. We can't let today, we can let today be a low energy day, but we cannot let today be a disengaged day. Because guys, and again, I know we talk about this a lot. This unit, it's hard. But guys, because it's hard, I'm always thinking about ways to do this better. And frankly, last year, in this moment of brilliance, it was seriously like the clouds parted, God's light shone down on me, there were trumpets and voices from heaven. Guys, seriously, I figured out how to teach this in a way that is going to make you crazy successful on something that is traditionally, statistically, really hard. And so, guys, I'm going to give you my stuff, and then we're going to apply it, and then we're going to talk a little bit about the factors that affect solubility, and then we're going to call it a day. So I think so today is going to be this. You are actually going to be answering questions during lecture as if you were taking the AP test. We're going to spend that time, and you're literally going to write longhand answers, John, in your very best penmanship, all the way through this as if it were a test. Because, guys, the questions that I'm going to ask you today are the hardest part of this unit. So, guys, let's make sure we're where we need to be, and then let's move on from there. So, guys, this is where we started, and we started with this idea. Let me see if I can write that we've got polar and non-polar solutes and solvents. So, guys, this is the 11-second review. Hold on to your hats. So, guys, one of the things that we talked about were within forces. And guys, when we talk about within forces, we mean the intermolecular forces or the bonds within the solute and solvent. So guys, quickly, what are the IMFs within water? Hydrogen forces. What are the IMFs within gasoline? Induced dipoles. Then guys, what about the forces within salt? Ionic bonds. And then, guys, the forces within oil, induced dipoles. Okay, so then at that point, we moved on and we talked about the forces in between. And guys, we got to this point. When polar water hooks up with polar salt, guys, what are the forces that are at play between them? Ion dipole. And ion dipole forces are strong, and that makes this soluble. Yes? Then we talked about induced dipoles. Sorry, this is ionic bond. Induced dipoles interacting with ionic bonds. What are the forces that exist between the induced dipoles of gasoline and the ionic bonds in a salt? They're functionally, and please don't say that. Please don't say there are no forces. What you want to say is the intermolecular forces that exist between gasoline and ions are very weak. Therefore, this is non-soluble. Then, guys, water and nonpolar oil. What are the forces that exist there? Very weak forces. Therefore, this is non-soluble. And really, technically, maybe the water does do a little bit of induced dipole with the oil, but it's not strong enough to dissolve. But then, guys, nonpolar to nonpolar, what are the forces there? They're induced dipoles. But these induced dipoles happen on a very grand scale. And as a result, these forces, as they permeate, as they propagate throughout the solute and the solvent, allow them to dissolve. Is that a good review? We okay? All right. So guys, with that said, this then. Oh, please, sorry, just a second. Let me see if I can go back without, go ahead.
I'm just wondering why, like, when you put oil into water, it does feel like kind of like a heat up, and you can get it to like get the smaller pieces. Is breaking that, is that just like friction, or does that have to do with it?
That's a great question. And so the answer is that's the balance. So let me see if I can repeat your question in case people didn't hear. So when you put oil and water together, why does the oil like bead up on the surface? So there's a lot of stuff to talk about. First of all, why is the oil on top? It's less. Now be careful with lighter. It's less dense, right? Don't confuse light with density. So you could have a drop of oil and you could have a swimming pool full of water, and the water's heavier. It's not light and heavy. It's dense and less dense. So the oil is on top because of density, right? But now we've got the interplay between adhesion and cohesion. So the oil drops are very, very cohesive. The same intermolecular forces that make the boiling point of oil like 1,000 degrees are also the intermolecular forces that make oil clump up. And so as a result, because there aren't intermolecular forces really between the oil and the water, there's not a lot of adhesion. The cohesion between the oil molecules causes it to clump up.
And what we call, like, if you have an oil drop, like, and you shake it, it's basically the small
Just a second. So like this, right? So this is oil on top and water on the bottom. So with food coloring in it. So here, you show us what you're talking about. Yeah. Yeah, so is that dissolving? When you shake, it's not, wow, that separated. Holy buckets, that separated fast. So all that you're doing is you're dispersing one inside the other. But still, even, so remember when we talked about the idea of interfaces? And here we have one very clean interface, but when we do this, we're distributing the interfaces. We're making smaller drops of oil and smaller drops of water. But still there aren't adhesive forces between the water and the oil, and so consequently they separate again. And so really what you're doing is it's just beating up within the water rather than on the surface of the water.
So is it like the energy of shaking it that's splitting?
It spreads them out, yeah, and then they come back together. Yeah, absolutely. And I don't know if they would throw this at you on the AP test, but maybe we should talk. There are some things that don't dissolve in water, but they also don't separate. Are you guys familiar with that? A great example of that, if you have a hot tub, is the yuck in your hot tub that causes it to foam. Actually, guys, what you've got is you've got oils that are in such small globs that they aren't dissolved in the water, but they are actually suspended in the water, and they don't precipitate. They don't fall to the bottom. You guys have never heard of this, right? They're called colloids. And so a colloid is a mixture that doesn't separate, but it's not dissolved. So if you get into biology, you're going to talk about colloids a lot in biochem. I don't think they'd ever throw it at you on the AP test, but guys, a colloid is a mixture that is not dissolved, but it also doesn't separate because the things that are in the mixture are so small that they still get hydrated and the water molecules surround them so they don't separate. Yeah. That's an interesting question. Does everything in hot chocolate dissolve? And my guess would be no. I would think it is a colloid, but let me give you a better example of a colloid that maybe is more definitive. Milk. If you buy 2% milk, that means 2% of the stuff in that jug of milk is actually fat. But I don't know if have you guys ever read the side of a milk carton? It says homogenized milk. What they actually do is they either do this through heat or they do it chemically. Because fats are big, long molecules, right? And fat doesn't dissolve in the water that the milk, the sugars and everything are dissolved in. So if you have milk out of the cow, the fat actually rises to the top and the rest goes to the bottom, and then you can skim that off and make butter. But in homogenized milk, they chop up the fats inside the milk so that they become a colloid. And so 2% milk is actually not a solution, it's a colloid. Because they chop up, again, the fats so that they can be suspended in solution. And it doesn't separate even though it's not dissolved. So there you go. All right, guys, are you good on these ideas? Yeah? Were you a part of this conversation on Thursday? Okay, keep going.
So is it polar and big enough that?
Yes. Who? Yeah, we were talking about this. So, yeah, sorry. Did you sneak up? Somebody snuck up and they were, grab your books. Sorry. Guys, if you grab your books and maybe, Jonah, you can get us there more quickly. I don't even remember what chapter we were in. And it took me like 11 days to find soap in the index. Still struggling. Oh, wow. Good for you. 10:07. Okay. So looking, Jared, at the bottom corner of 10:07, where it talks about stearate, 1007. So guys, down in the bottom right corner of page 1007, there's actually a molecule down there called stearate. But this can be thought of as two different molecules tagged together. So I don't have my book in front of me, but the tail goes down diagonally to the right? Guys, if you look carefully at that tail, you'll notice that it's crazy symmetrical and therefore nonpolar. So if you're looking just at the tail, what are the intermolecular forces that exist? Those are induced dipoles. And guys, the induced dipole of that long tail is very, very attractive to oil. But then if you look at the head, if you will, of that molecule, you'll notice that you've got polar oxygens, and even, are there hydrogen bonds maybe available? Oh, it lost the hydrogen. But you'll notice that we've got oxygens down there. We've got dissymmetry. We've got the place for dipole forces to form, and maybe even hydrogen bonds. And guys, that end is very polar and therefore attracted to water. So guys, if you've got grease on your hands and you run it underwater, nothing happens, right? The reason, of course, is because of this. Water does not dissolve things like oil and grease. So what soaps do is they provide a link between water and oil. The polar end, the bottom right corner, the polar end is very what we call hydrophilic, water-loving. It's polar. The other end, the long end, is hydrophobic. It doesn't love water. It's induced dipoles, but that can form the bonds or the intermolecular forces that allow oils to dissolve in things like gas. The same things that are at play here, and that's what soap does. So if you look at your soaps and your shampoos, you will see stearate salts in your soaps and shampoos, and that's why. Yeah. Yeah, absolutely. Yeah, definitely. Yeah. But understand soaps also have a lot of other things in them, fragrances and all this other stuff. And so, but yeah, absolutely. You guys, is that, yeah? Flour?
Yeah, like, you think like oil and water and stuff.
Yeah, you've actually made a colloid. Yeah, unless there's something long chain enough. So flour's carbohydrates, right? And carbohydrates are long chain things. So maybe the oil is connecting to the No, carbohydrate's way too polar. I think you're just making a colloid, a suspension. Okay. Guys, a little off track, right? But guys, the reason that I supported and encouraged this whole conversation is because it's exactly what your brain needs to be wrestling with. I love all the what ifs. I love the hey, is this hows? Because guys, you're going to see that they're going to throw interesting and at sometimes counterintuitive examples of these things at you, and you've got to be able to think through them. So guys, what I want to do is this, and please don't write any of this down, just watch. So guys, this is the heavens opened organizational way for you to think about this. You need to think about within forces, and you need to think about in between forces. So guys, within forces are the intermolecular forces within an individual substance. The in-between forces are the intermolecular forces that exist between two different substances. So guys, with that structure in mind, again, please don't write this down. But guys, with that structure in mind, let's do this. So guys, the big question then is this. On the test, and if you want to write it down, you can. The way to approach these questions in your brain is to ask yourself, is this a within question or is this an in-between question? And so guys, when we talk about within questions, what we're talking about are things like boiling point, melting point, freezing point, vapor pressure, volatility, all of the characteristic properties of a substance. Why does this melt at a high temperature? Why is this not that volatile? Things like that. Guys, those are within questions. Then you're going to get in between questions. And guys, when we talk about in-between questions, it's usually solubility. I can't think of another example other than solubility. But guys, the way to approach this then is this. If it's a question about boiling, freezing, melting, volatility, whatever, only talk about the forces within the substance. And explain why. This has dipole because it's not symmetrical, whatever. If it's an in-between force like solubility, only talk about the force between the solute and the solvent. You're going to do this concisely. You're going to do this rhythmically. Don't say too much, but answer the question. So guys, these questions always come with this caveat. Explain based on molecular structure. These questions on the test, ours and the AP, will always come with the caveat, explain based upon molecular structure. You guys okay? Okay. So guys, if you need another sheet of paper, you're going to need probably the better part of a blank sheet of paper in order to do what we're about to do. No, I think just front. But guys, here's the deal. It's the first Monday in May. You were with me minutes ago. You had a lovely build your own taco lunch. You're all fueled up, fat, dumb, and happy, and ready to go take the test. You just got done with 90 excruciating minutes of multiple choice testing. And then you came up, actually no, they won't let you guys come up and talk to your teachers anymore. It used to be that between the multiple choice and the free response, I would have like juice and crackers and stuff for you. But we can't do that anymore. There have been changes. Last year. Yeah. Yeah, to be honest with you, it turns out it's been the rule for years and years. We just didn't have an AP coordinator that actually knew the rules, and now we do. So we've been doing this illegally. And then, guys, you go back in, and now it is time for an hour and 45 minutes. That is 105 minutes. An hour and 45 minutes of free response questions. There are 7 of them. 3 are long form, they take you about 20 minutes. 4 of them are short form and they take you about 10 to 12 minutes each. We'll do the math later, but the next thing you know, you're an hour and 45 minutes into this test. And guys, somewhere in that test, you are going to get questions that typically go like this. They're going to have you draw Lewis dot structures. They love to start there. But then, guys, after you've drawn the Lewis dot structures, there are follow-up questions like this. And guys, you are now going to answer these questions. They come in multiple pieces. So question number 1 is this. What intermolecular forces exist in liquid water? Write your answer. Based upon molecular structure. We're going to start simple. What are the intermolecular forces that exist in water? Guys, how do you start this answer? All of you start them the same. The IMFs that exist in water are, and then because. But you always start by answering the question. Always start with the IMFs in water are. Start there. Write incomplete sentences. And John, there's probably a way that you could craft another way to start the sentence, but that involves thinking, right? So seriously, rather than think, get in the habit of always starting your sentences by simply restating the question. It takes 3 or 4 words and it gets you started. And frankly, it makes the AP graders think you're smarter. And then, guys, again, the part that I left out of all the questions that I'm going to present you with is the part about explain based on molecular structure. All right, so guys, you should be done. You done? This should be 1 sentence, maybe 2. You guys done? Okay. Trade with the person next to you and let them read your answer. Taylor, you can move back. Share these and let the person next to you read your answer. All right, guys. So this is not going to take us the entire class period, so we're going to transition relatively quickly. But guys, here's the deal. You're going to see this question presented to you 2 different ways on the AP test. You'll also see them on the test we're taking over this unit in the not too distant future. Guys, sometimes they will say this, list the intermolecular forces. Guys, kind of to John's point, if the question says list, do not write a sentence. But if the question says list, it's safest to list all of them. Everything has induced dipoles, right? Yeah. So if you were to list the intermolecular forces in water, we would go induced dipoles, dipole, and hydrogen forces. If you were listing them, you would list all 3. But if they're asking you the question like this, what you quickly find out is that it's a part of a bigger question. You'd be able to see the whole question. So when they ask it like this, they're really looking for the intermolecular force that has the greatest impact on the large scale structure of water. And sometimes they'll even say it that way. It'll say, what is the predominant intermolecular force? But in either case, it goes like this. The intermolecular force that exists in water are hydrogen forces. This is present because water has hydrogens bonded to highly electronegative oxygen, allowing for hydrogen forces. So you've got to mention hydrogen forces, and then the molecular Y is hydrogen bonded to oxygen or nitrogen fluorine. Just a second, go ahead, Claire.
Can you discriminate between
So the better term is unshielded, but you get to college and everyone just calls them naked protons. So I would imagine the first time naked proton crosses the desk of one of the graders, they would send it up to the table leader and say, hey, what do we do with naked proton? This is literally how they grade these things. And then they would conference over it. And if they couldn't decide at that level, they would send it to the person that wrote the question. But I would be all but certain they would go, hey, here's an exception. Naked proton works for unshielded. But your better term is unshielded. Jared? Okay. You guys good on that? Right. No, and that's what and so again, there typically in these questions, there are multiple questions, and there's it's called a stem. There's an introduction to the question. And the introduction to the question will always say, answer the following questions based on molecular structure. It's always I just didn't put it in here, but yeah, go ahead. Absolutely, yes, most definitely. They won't do that. Again, I wrote these. They won't on the test, but you can in your answers.
Do we even mention that oxygen is highly electronegative, or do we say hydrogen bonded oxygen?
That's interesting, Michael. Is that...
Like if we say that the bond is created,
So, yeah, let me to that thought, Claire, be careful using the word bond when you're talking about IMFs. Even though I know that you're talking about the hydrogen-oxygen bond, if you get a couple words out of order, they're going to think that you're saying that there are bonds between the waters. Really shy away from using the word bond in these answers. But Michael, to your point, I don't know. Would they allow you to just say... So I would think that if you didn't say highly electronegative oxygen, then you would have to say hydrogen is bonded to oxygen, which creates an unshielded proton. Somehow or another, there needs to be something about that electron moving away from the hydrogen. Whether it's based on strength and electronegativity, or Claire, whether it's based upon unshielded, I think you should probably mention it in one case or the other. My question is, would they mark it wrong if you didn't? It's not a chance I'd want to take. Okay. All right, guys, then this. What are the IMFs that exist in cooking oil? No, you want to just write as sloppily and as incoherently. And if you can make your handwriting really bad, yeah. No, sometimes what you want to do is just, or write in your non-dominant hand.
That makes a lot of sense.
It does. Yeah. Because anything you can do to make yourself look uneducated in the eyes of the grader.
Yeah, because if they can't understand what I'm saying, they'll just give me advice.
Yeah, right. Exactly. Because that's what we do in high school.
Because I didn't try to write in French.
I'm glad that you all understood that that was frighteningly tongue-in-cheek.
Right. But like, they won't talk maybe so much about missing period, right?
No, but so realizing that the people that are grading your test are tired.
Yeah.
And they finally get to the point where they're looking for any reason to give you the benefit of the doubt. And organization, penmanship, make you look smart and therefore give you more of the benefit of the doubt. So, no, they won't mark it wrong if you're missing a period, but they may read it more closely. All right, guys, so you should be done with this one as well. Again, and John is absolutely right. There's 1,000 different ways you could start this sentence. But guys, again, right, I shared with you, the AP test is tomorrow. And we are increasingly getting ready to think about how to think about this test. Because you guys understand this, right? Passing the AP test has very little to do with how much chemistry you know, and a lot to do with how good you are at taking this test. And so, guys, rather than think, what's a great way to start this sentence? What if you just get into the rhythm of starting the sentence by restating it? The IMFs that exist in cooking oil are. Then the answer is induced dipole forces, because the oil molecules are large and nonpolar, making them polarizable. You need to mention large. And you need to mention something about symmetrical or nonpolar or something like that. But Linz or Clara ask an interesting question. Do you have to talk about why the other forces are not present? And the answer is no. You just need to establish that oil, you could even say is large and polarizable, large and nonpolar, but you need size and you need polarizability. Yeah. Because it's the argument, and actually you're right. At this point, that's interesting, Joni. You don't. The reason I'm mentioning it is because I know what the next question is. And so you're absolutely right. You don't need it. You actually just need, thank you, nonpolar and polarizable. You don't need size. Now you do. Why is water more volatile than cooking oil? Guys, big deep breath on this one. Why? Think before you write. Of course, you already know what your first words are going to be. Water is more volatile than cooking oil because. Yeah, and you know what, John, I don't disagree with that, but yeah, and frankly, yeah, it cuts out the variability. Yeah, I like the way you said it. Let your brain get going. So guys, this one probably required maybe an extra sentence or two. You guys okay? Not quite yet. Can we talk? So guys, I have a question for you. I'm going to just call them 1, 2, and 3. Question number 1, is this a within or an in-between question? Within. The forces within water. Question number 2, within or in between? Within. Question number 3, still within. So we are not talking about why does cooking oil not dissolve in water? We're talking about why is water more volatile than cooking oil? So guys, this is still a within question. So here's what that means. You have to talk about the forces within each of these substances. Now, we have an advantage in this question. We already did. So guys, if you are not going to say again that water exhibits, and that's the word you want to do, please do not say water has hydrogen forces. Water exhibits hydrogen forces. That's your money word right there. Water exhibits hydrogen forces. Oil exhibits induced dipoles. If you don't want to say that, you can reference them in the previous questions. And we'll talk more about how to craft that into a sentence. But guys, the deal is this. If you're going to say that water is more volatile than cooking oil, it's all about the forces within, and that's the important point. So now, guys, let's talk loosely about the answer, and then we'll craft it into a good sentence or two. So guys, this is counterintuitive for 2 different reasons. Every single property that you know of a substance varies directly with IMF. Think about that. Every single property that you know of a substance varies directly with IMF. The stronger the IMFs, the higher the thing. Freezing point, melting point, boiling point, condensation point. Guys, all of those vary directly with intermolecular force, except for volatility. Volatility is the only characteristic property of a substance that varies inversely with IMF. So there's hiccup number 1. Guys, here comes hiccup number 2. Which one do we think of as being stronger? Hydrogen forces or induced dipoles? Hydrogen forces. So now, guys, we've got a double, triple, quadruple whammy. Because fundamentally what we're arguing then is that which one has the stronger intermolecular forces, the oil or the water? The oil does. Let's think about it the other way. If something is more volatile, what is true of its intermolecular forces? It's weaker. So maybe that would be the cleaner angle to take in this. We know that water is more volatile. Therefore, water's IMFs are weaker. Yes? So now how do we pull that together? And guys, I would say something like this. Water is more volatile than cooking oil because the hydrogen forces in water are weaker than the induced dipole forces in the cooking oil. End of story.
Do you need to talk about the shapes?
Don't need to. Yeah. Yep. It wouldn't, and again, this is why we started thinking size, right? We understand why. But they don't expect you to, they're okay with us just going, yeah, that makes sense. Even though in the back of our mind we're going, wait, that's unusual. And it is, because hydrogen forces 1 to 1 are stronger. It's just the oil molecules are so stinking big and boogly that we end up with stronger, just like in intermolecular forces. But guys, you can just state it as if, well, sure. But it's got to be the water's more volatile, because its hydrogen forces are weaker than the oil, the induced dipoles. You could say it the other way. You could say the induced dipoles in oil are stronger than the hydrogen forces in water. Either way is fine. So, yeah. Yeah, so So this is where we've got to be careful, because you truly are guilty until proven innocent. They are looking for a reason to take the point away from you. And it's only 1 point. There's no partial credit on the test. So it's not wrong, but then you need to ask yourself, is it necessary? And the answer in this case is no. That said, I know, Clara, that creates a little bit of dissonance, right? Because you're going, wait, how do I know what we need to say and what we don't? And the answer is, I will guide you in that as we're doing tests, as we're doing things. But then, guys, remember, we're going to spend an entire month working on questions off of old AP tests. And I'm going to give you the grading rubrics. And you're going to very quickly get really comfortable with, okay, I know what I need to say, and I know what's too much. So we're moving towards that.
Basically, as concise as possible.
Absolutely. Say enough and no more. Yeah. Yep. All right. We good?
So the higher the IMS, the higher the viscosity, right? Is that-
Yes, with one problem. And I've never seen a viscosity question on an AP test. It's not a major idea. But understand that intermolecular forces do trend with viscosity. The higher the viscosity, the higher the IMF, the higher the viscosity. But that's not the major predictor. The major predictor of viscosity is molecular size. But I've never seen it. Yeah. Yeah, but again, viscosity you don't see a ton of. Yeah, but don't confuse that with volatility. Right, volatility is the ability to evaporate. Yeah? Okay. All right, guys, set number 2. Benzene is a liquid at room temperature while paradichlorobenzene is a solid. Explain it. Hey, this sounds a lot like the last lab we just did. You know, it's up to you. I mean, maybe this one is long enough that it just, but maybe what you could do, what I would consider doing is making it 2 sentences. Benzene is a liquid at room temperature because paradichlorobenzene, p-dichlorobenzene is a solid because. That might be a more effective approach. And again, as Elizabeth really brought home, the stem of the question is based on molecular structure. Guys, forgive me for interrupting, but I have a question. Never mind. You can figure it out. Let me just say this, though. They would not expect you to know what paradichlorobenzene is on the AP test. The only reason I felt comfortable asking is because we used it in lab. If they were to ask you this question on the AP test, they would give you the Lewis dot structure for both of these. The only reason I didn't is because we've looked at them previously. But they would give them to you on the test. As a matter of fact, there's a question on the test for this unit where they give you the Lewis dot structures. Yeah, actually. Huh. Again, I just wrote these this morning. I should be a teacher. sobering because there was a moment in my life 34 years ago, where I thought to myself, I should be a teacher. And here I am. So guys, let's go for about another 10 seconds. If you're not there, and again, the test is tomorrow, but we're working towards this. Guys, we need to get good at writing, but also writing quickly. You'd be amazed at how fast 105 minutes goes. We okay to talk? We're going to talk. So guys, it goes like this. What do we know about benzene? Symmetrical or non-symmetrical? And again, you wouldn't need to know this, but it is. They would give you the structure on the test. But is it fair for me to do that? That's benzene. Actually, what they would... so what they would give you on the test... And this isn't a great example because, in fact, it's not alternating double and single bonds. Alternating double and single bonds is actually called cyclohexane. It doesn't resonate, but when it does resonate, it's benzene. So they would not. This molecule is not a great example because you'd have to draw its resonance forms anyway. But benzene is nonpolar. Therefore, what are the intermolecular forces that it can exhibit? Induced dipole forces. These induced dipole forces are strong enough to hold this together as a liquid. Yeah? Then, guys, within paradichlorobenzene, dichloro, and again, they would give you the Lewis dot structure. But from our experiences, we know that there's chlorines on opposite sides of this thing, and these chlorines make these molecules polar. And because they are polar, what are the intermolecular forces that exist within? Dipole-dipole forces, and that holds them together as a solid. Guys, with that said, and this isn't a part of the question, but it's interesting. Guys, benzene has an amazingly, let me say it differently. It's crazy volatile. Did I show you what we did with the stuff from the lab? We poured it in a beaker, right? It was gone the next day. The benzene just evaporates like crazy and it's gone. And then, guys, the paradichlorobenzene just stays behind as a solid. But remember how didn't we talk about the hockey pucks from the toilets? They smell like crazy because they're actually sublimating. The paradichlorobenzene's intermolecular forces are fairly weak and it sublimates. So we good? So we've got induced dipoles in the benzene, holds it together as a liquid. We've got dipole forces in the paradichlorobenzene, and good to go. Wait, was our solute benzene in the lab? Or was it? It was benzene, right? Oh, it was cyclohex. But that guy's also, and again, they would give you the structures. Again, cyclohexane just doesn't resonate, which would make it a better example. But it too is also polar in there, or is nonpolar and therefore induced dipoles. But guys, this paradichlorobenzene dissolves in water. Paradichlorobenzene dissolves in water, while benzene does not. Frankly, they would never give you this in either case, but technically it's fine either way. Guys, before you start writing, let me ask you a question. Question number 1, within or in between? Within. Question number 2, in between. So guys, when you've got in between questions, you need to identify the intermolecular forces that exist only between the solute and the solvent. Did that go okay?
Yeah, some couldn't do this back home, and I started talking to them, it's a repeat question. So.
Oh, thank Thank you. You're a genius. Why don't you just come and teach this class and I'll take a vacation? Thank you. The which? The three. Oh, yes. Oh, no. Oh, yes. No, bad. So, guys, please don't let this freak you out, but I switched cyclohexane for benzene, just so that, again, I wrote these this morning. No, because they're both symmetrical and therefore nonpolar. They both are induced dipoles. So guys, when we're done with this, we're going to do one more set of questions. And then we're going to move on and we're going to talk about the things that influence solubility, specifically pressure and temperature. And then guys, we've got a couple days on gases. And then we'll have to talk about how we wrap up this unit relative to our 4-day weekend. I know. We'll figure it out. I know. Although it's funny, and maybe we already talked about this, a lot of us as teachers talk about that year right after COVID shut down the schools, where we had Monday, Tuesday, Thursday, Friday, and they were all short days, and we had Wednesdays off. For a lot of us, it was our most productive year in our careers. We got more material done in 4 days than we do currently in 5. Yeah, it was awesome because we were able to condense the material, and then kids in their brains, when it becomes 2:15, the only thing in your head is get me out of here, right? But when school's out at noon, the thing in your brain is, oh, I have time and energy to come and get help. And our classrooms were full of kids going, hey, I don't get this, I need help, I need support. And then on Wednesdays, when we didn't have students, we were caught up in our grading. We were giving immediate feedback to our students. It was amazing. It was so good. Yeah. Well, everybody liked it. Everybody voted for it. When the district sent out that survey, everybody voted for it, and they ignored it. Yeah, they ignored all of the data and said, we're going to do what we wanted to do anyway. One of the few times I've seen Alpine District not be receptive to input. I was disappointed. And it wasn't the leaders of Alpine School District, it was the school board. And they don't get it. Yeah, absolutely. Right? Oh my gosh. Yeah, Britt and I, Miss Call and I sat down and did the math on how many days last year we had to waste because of, remember when they started taking days out of the calendar, but then let it be 2 A days, 2 B days? And when they shortened Wednesdays to the point, like they are now, that they're crippled, we lost 19 days of class last year trying to make up for that. Amen. All right, guys, so here we go. Paradichlorobenzene dissolves in water. What are the forces between water and paradichlorobenzene? Dipole, dipole. Why are they not hydrogen forces? Because guys, whether it's cyclohexane or whether it's benzene, doesn't matter. There ain't no hydrogen, oxygen, or nitrogen in there. It's dipole, dipole. So maybe you would say it like this. Again, you said benzene. Perodichlorobenzene dissolves in water. Ooh, maybe say it like this. Polar perodichlorobenzene dissolves in polar water because of the dipole-dipole forces. Huh? Right? Or maybe you could say perodichlorobenzene and water are both polar, allowing for dipole-dipole forces. However, but then we go on to the next one. Cyclohexane does not dissolve in water because any intermolecular forces that exist are weak. And actually maybe we should identify non-polar cyclohexane does not dissolve in polar water. That's a great way to do that. Non-polar cyclohexane does not dissolve in polar water because any IMFs that exist are weak. If you wrote that, it would bring a tear to the eye of your grader. Yeah. Yes, absolutely.
I was saying that like the water molecules don't induce a dipole.
They don't because water is so locked down that it isn't big enough to push around the electron clouds of something like oil, right? I mean, water's like, ding, it's pretty locked in. It's not very sloshy.
Not too far to go.
Yeah. Okay, guys, we're going to do one more. You ready? Here we go. SO3 boils at a higher temperature than SO2. Hey! I love that you're making the connections. This is straight out of the homework. They won't grade your Lewis dot structures, but I couldn't answer the question without them. I also really love that Lindsay's question a minute ago was, is this a within, or can forces be a within and an in-between? It means you're starting to, at least at some level, buy into this way of thinking about these. By the way, guys, is this a within or an in-between? It's a within. It's two, but it's boiling. It's a within, but it's two of them. Yeah, actually, Claire, I did lift this directly out of that question, didn't I? The one that you asked about last time? Look at me being all crafty. Guys, I can't tell you how happy it makes me that we're doing this. This is the first time I've done this in 20 years of teaching AP. It's something I've always, I mean, it seems so obvious, but I love that I'm always getting better at this. Eleanor, do you remember when we did this last year, 2 years, and it was like all of this? Are you even listening? Do you know what we're doing? And remember how we used to talk about the force within and the force within and the force in between and the sum of the two, and just created this entire scaffold that we really didn't need? Yeah, I deleted all of those slides. Yeah, this is so much better. I know. That's where it came from. The within and in between was when we were doing test correction and so on. I was struggling to figure out how to get you guys there. Yeah. I love that you remember that. this does. All right, so guys, let's talk. Yes, both of these molecules resonate, but fundamentally, guys, this is good enough to get us to structure. So we are talking about SO3 first. It's sort of a disaster on the board, but it is trigonal planar. And the resonance makes it even more exactly trigonal planar. Because guys, if this were a localized pi bond, again reviewing for the test, if this were a localized pi bond, these angles would expand a little bit. But because it's a you don't need to know that, but because it's a delocalized pi bond, it is very trigonal planar. So guys, if it's trigonal planar, is it symmetrical? Yes. If it's symmetrical, is it polar? No. So what are our IMFs? Induced dipoles. So guys, where do you need to engage in answering the question? And we would say SO3, well, let's just talk IMFs first. We would say that SO3 is non-polar, therefore its induced dipoles or its IMFs are induced dipoles. Then guys, SO2, what is its molecular geometry? Bent. And guys, because it's bent, it is polar. Because it's polar, what are its IMFs? Dipole-dipole. So then, guys, we got to bring this together as an answer because this is something that initially is counterintuitive. Because, guys, this is induced dipoles, and this is dipole-dipole. And again, you don't have to talk about the counterintuitive nature of this. You just need to say it. So SO3's induced dipole forces are stronger than the dipole-dipole forces that exist in SO2. Therefore, SO3 boils at a higher temperature. I was just thinking about as I said it. It's not wrong, but I really don't think they would get you for it because what they're really asking you to get to is the IMFs. It wouldn't be wrong to say non-polar SO3's induced dipoles, but I think if you just said SO3's induced dipoles, I think you'd be okay either way. Yeah. You guys good? Okay, so following up. Last question. Guys, why does SO2 dissolve in water and SO3 doesn't? Is this a within or an in between? In between. You guys know what the word ruminate means? Okay. Ruminate? Yeah. Yeah.
I just want glass onion to be saying all the big words. It's like, we just think we should breathe. Infraction.
All right, guys, can we not quite yet? Okay. All right, guys, let's talk. So it goes like this. So SO2 is polar. Water is polar. So what are the forces in between? Dipole, dipole. So maybe our first sentence would be this. SO2 dissolves in water because both are polar, therefore exhibiting dipole, dipole forces which allow it to dissolve. Then SO3 does not dissolve in water because the forces that exist between non-polar SO3 and polar water are not strong enough to allow it to dissolve. You don't have to name them. If you wanted to put the polarities in front of them and say something like non-polar SO3 does not dissolve in polar water because the forces are not strong enough, that's fine. But at some point you need to identify the polarities and then the forces in between. Is that okay? Okay. So guys, seriously, that is probably one of the most meaningful things we've done in this class. They love to trip you up on this stuff, and I love the work that we just did. So guys, we've got about 5 more minutes and we're done. You ready? Okay. Imagine that we have a beaker of water. Guys, just watch. We're moving on. Don't miss this. Imagine that we have a beaker of water, and imagine that we want to dissolve solids and gases in that water. You ready? Okay. So here, let's just draw a picture. Draw a beaker with me, shall we? Say yes. There you go. Or you could say, we shall. Oh, yes, let's. All right, guys, so it goes like this. Imagine that you've got a beaker of water and you add some salt to that water. What do we call the amount of salt that maximizes the concentration of the solution and no more will dissolve? We call that saturation. And what are the units that we use to measure how much stuff dissolves in water? So the units are grams per 100 milliliters of water. So guys, then the question becomes this. Say that we know the solubility of whatever our salt is, and then we want to get more salt to dissolve in the water. What can we do? Heat up the water. There are a couple of exceptions. But guys, for the most part, the solubility of solids in liquids goes up with temperature. Did you already know that? So is there any reason to write it down? Okay, so, and maybe we could do this. Solubility goes up as temperature goes up. Then guys, what about pressure? What if we squeeze this harder? Like if we were to saturate this, so there's some solid at the bottom that hasn't dissolved, which now means it's supersaturated. Oh wait, we didn't talk about supersaturation, did we? This isn't supersaturation. I'll show you in a minute. It's saturated. Now, what if we were to put a plunger in there and squeeze it? Would more or less of this dissolve? Wouldn't change. Doesn't change. The solubility of solids in liquids is not pressure dependent. Are you good? Okay, what about this? Now let's take our thing of water and now let's dissolve a gas in the water. So guys, what can we do? Well, actually, let me ask it the other way. What happens if we increase the temperature? What happens to the amount of gas that will dissolve in the water if we increase the temperature? It goes down. The solubility goes down. This, guys, is why you don't fish in the middle of a hot summer day. The heat from the summer day keeps oxygen from dissolving into the water, and the fish are actually struggling to breathe. So the last thing they want to do is be running around looking for food. They wait until the evening and the night where the air cools down. The oxygen will more likely dissolve into the water, and then there's more air to breathe, and it's easier for them to be active. You guys know that? At least you understand this, right? The oxygen that fish breathe is not the oxygen in water. You know that, right? It's actually what's called dissolved oxygen. So as the temperature goes up, less gas can dissolve. Guys, quickly this. Why? What happens to the molecules in the water when we heat them up? They move faster. And can't you imagine these faster water molecules banging the gas molecules out of solution? Yeah. But then, guys, this. What happens to the solubility if we increase the pressure? The solubility goes up. This is why when you screw the lid off of your Dr. Pepper, it goes everywhere. Because, guys, when you screw the lid off of a soda, the pressure goes down. And as the pressure goes down, the solubility goes down, and all the carbon dioxide that used to be dissolved in the water can't stay dissolved in the water anymore, and it all comes gushing out the top, and it takes the soda with it.
What does shaking it up do?
Yeah, so actually what shaking it up does, so it's a very, so hydration, right? So in hydration, you've got liquid molecules, water, surrounding whatever is dissolved. Can you picture Babs talking about the thing, right? So the same thing happens here. If we've got oxygen or carbon dioxide dissolved in this, the water molecules are still surrounding the carbon dioxides. And they settle into this condition where it's sort of stable because it's not structure, but there is some sort of stabilizing order to it. But when you shake it, all of a sudden the associations, the hydration of the solution changes and the water molecules move around. And now the forces that used to allow those carbon dioxide molecules to dissolve, they've been disrupted. And so it actually decreases the solubility of the gas in the liquid. And then when you unscrew the lid, it's just, we're out of here because even less can dissolve. So are you guys familiar with the idea of the bends? Have you ever heard of that? Yeah, it's called nitrogen narcosis. And guys, what happens is this. When you go down to the bottom of the ocean, the pressure goes up, and therefore the solubility of gases in your blood goes up. And so as you're breathing air out of a scuba tank, you're still putting oxygen and nitrogen and all of these other gases into your blood through your lungs. The problem is that you're being squeezed by the water, and so more of these gases can dissolve in your blood. And then if you come up too fast, it's just like screwing the lid off of a bottle of Coke, because all of a sudden these gases can't stay in solution and they form bubbles. But those bubbles can't get through the capillaries in your circulatory system, and they create like little clogging points, and your circulation gets cut off, and it hurts like crazy, and you bend over in pain. That's where the name the bends comes from. So you guys get the ideas? So the solubility of solids in liquids is only temperature dependent. As one goes up, the other goes up. The solubility of gases is dependent upon temperature and pressure. As temperature goes up, solubility goes down. As pressure goes up, solubility goes up. Good? Okay. Eleanor, thank you. So guys, this and this and this and this and this and this and homework.